Ho, ho, ho. In this video, we are going to review Santa Claus's favorite coordinate system, polar coordinates. If we start at the origin, we already know that we can define the position of other points by using a Cartesian coordinate system based upon a certain distance x and then a distance in the y direction. In polar coordinates, we are also going to define the location of a point using two coordinates. The first coordinate is a certain distance from the origin, a distance r. And we note that this distance r defines a circle centered at the origin, a circle with a radius of r. Next, we imagine that this particular vector is rotated a particular angle, phi, in this direction, counterclockwise. Therefore, we can define the position of a point using two coordinates. The first coordinate being the distance r from the origin, and the second point being the angle phi. And these are the so-called polar coordinates of our point. We can interconvert between polar and Cartesian coordinates as follows. The x-coordinate is equal to r times the cosine of phi. The y-coordinate is going to be r times the sine of phi. So this allows us to determine the Cartesian coordinates that correspond to a particular set of polar coordinates. We can also go in the opposite direction. If we know the Cartesian coordinates, we can determine the appropriate polar coordinates. For example, the coordinate r would be equal to the positive square root of x squared plus y squared. An important thing to realize in the polar coordinate system that r can take values from 0 into the positive numbers. So r can never be a negative number in the polar coordinate system. So that's why we have to always take the positive square root to determine the coordinate r. On the other hand, we can determine the angle phi. This is the inverse tangent of y over x. So we can easily interconvert between polar coordinates and Cartesian coordinates. The next thing to keep in mind is that if we're working in two dimensions, one version of the Schrödinger equation is as follows. So we could have minus h bar squared over 2m times this operator del squared times c plus v of psi equals e times psi. So this particular operator, sometimes called del squared or the Laplacian, has a particularly simple form in Cartesian coordinates. So we can write del squared as equal to the second derivative with respect to x plus the second derivative with respect to y. That is this form that it has in Cartesian coordinates. We'd also like to be able to write this particular operator in polar coordinates. So in polar coordinates, it's going to have a slightly different form. And the form that it has is as follows. Del squared in polar coordinates is going to be equal to the second derivative with respect to r plus 1 over r times the first derivative with respect to r plus the second derivative with respect to phi. So this is the form that we're going to need for problems in quantum mechanics for which we're going to use polar coordinates. I thank you very much for your attention. Have a good one. Ho, ho, ho.